Okay, hey everybody. This is the week 3 supplemental lecture video for stats. So a bit of a hodgepodge of things in today's lecture. We're going to finish a couple topics in 3.1, a couple minor topics, the weighted mean, geometric mean, and harmonic mean. We're going to finish up a couple of minor things in 3.2. So range, rule of thumb, and coefficient of variation will go pretty quickly. We'll go through an Excel demonstration for 3.1 and 3.2. We saw a little bit of 3.1 in class already, but we'll review that and do 3.2. And we'll talk about Chebyshev's theorem and the empirical normal rule to finish out 3.2. And then we get started on 3.3. In next week's campus class on Tuesday, we'll do one more example of computing the variance and standard deviation of the salary data by hand. And then we'll finish up section 3.3, finish up percentiles that we'll start today. We'll discuss skewedness and outliers and talk about the 5-number summary and box plots. And we should have enough time on Tuesday to get a start on chapter 4 as well. Okay, so let's get started then. So we talked in 3.1 about measures of center, for instance, the mean, the median, and the mid-range. We introduced these ideas. We computed mean, median, and mid-range for the 3 data sets we've been working with. And we talked about how they're all 3 measures of center, but things like outliers, particularly skewedness, can affect them. So we see that there are a few different measures of center we've seen already. There's a couple others as well. In fact, there are a lot others, but there are a couple others that we will talk about. One of them is the mode, which I think we mentioned briefly in class, but I want to do a bit longer of an example here. The mode is the most frequently occurring data value. Now, where is the mode super nice? Well, the mode is super nice in a couple of situations. One is with categorical data. Categorical or nominal. So for instance, let's say we had shirt color and we had some different colors, blue, red, let's say yellow and green. So these are the different classes, the different possible outcomes. And the frequency, let's say we had 24, 13, 2, and 7. So if we wanted a measure of center for this data set that might just look like blue, blue, red, blue, green, blue, yellow, and so on. If we wanted to compute a measure of center for this, well, if we try to do something like the mean, we'd be trying to add like blue plus red plus yellow. Clearly, that doesn't make much sense, right? This is nominal data. It doesn't have enough structure to really add anything. In this case, we just have letters and we can't add, but even if we had numbers like, say, a zip code or something like that, that is still nominal, maybe we could like add the numbers together, but that wouldn't be a sensible thing to do, right? Computing an average zip code doesn't make sense in that case. So we wouldn't want to try to get something like the mean as a measure of center for nominal data, even if we could kind of force the issue and take something that looks like a number and treat it like a number. The same goes for the mid-range, right? Add 2 data values together, divide by 2. We can't add our data values. Doesn't make sense here. The median might be a little more forgiving, but here we need to have at least the amount of structure that we can impose an ordering, a natural ordering or ranking. And in this case, we can't even really do that. There's not a natural ordering or ranking to these colors, at least not in this context. So we don't even have enough structure to order them, so we can't compute a median. However, we can compute a mode. We can always just count the number of occurrences of each class. That gives us frequencies. And these frequencies themselves are kind of nice numbers. They are sensible numbers. Like the number 24 means something numerically, right? So these numbers, these frequencies are ordered. We can, do mathematical operations on them. But in particular, they have an ordering, and I can observe that the frequency 24 is the highest frequency that I observe. So then I would say that the mode, and we want to be careful here, the mode isn't 24. The mode is the data value associated with 24. So in this case, it would be blue. So maybe more people wear blue shirts than wear any other color of shirt from the colors that we're looking at here. So for something like nominal data, about the only measure of center in a sense that we have is the mode. The other place that the mode actually works pretty nicely is if I have a ton of data. In fact, I might have like a data that's modeled by the continuous curve like this. The mode is going to be the x-coordinate of the peak. And it turns out that with a little bit of math, it's fairly easy to find peaks of functions. So in examples like this, the mode is kind of sensible. The mode does have some downsides, though. So it does have some downsides. I could compute a mode for, let's say, for data that is numerical, that has maybe a natural ordering. I could have maybe dice rolls 1 through 6 and frequency of occurrence. Now I see that this is uniform data, right? In kind of a perfect world, I would have a histogram that looks like this. But of course, if I roll a die a bunch of times, if I say roll a die 100 times, I can't get exactly 1/6 frequency in each of the bins 1 through 6. But even if I were to roll them, say, 60 times, where it would be possible to get exactly 10 of each, even if the die is perfectly balanced, I expect that I might get a couple fewer of this number and a couple more of that number. So if I did something like 60 rolls, I might get something like 12, 10, 9, 8, let's say 11 and 10. I think that adds to 60. Yep. So maybe I get something like this. So maybe in reality, this one's a little higher. This one's a little lower. This one's a little lower. This one's a tad higher. Well, now I note that my mode is 1, right? But for something that I expect to be a uniform distribution, this is basically just random, right? I could have just as easily gotten 12 6s and 10 1s, and then my mode would have been 6. Effectively, in kind of a worst case scenario where I have uniform distribution underlying things, my mode is basically just a random draw. It really doesn't have any sense of being in the center of the distribution really at all. I also have an issue that, let's say that I had gotten an 11 here, an 11 here. Well, now there's more than one class that has the quote highest frequency. Sometimes when this happens, when there's kind of two clear humps in the distribution, we might call it bimodal, because these distributions come up sometimes. But in this kind of a situation where I have 6 possible outcomes and I have 2 or 3 or something of the outcomes, 2 or 3 of the classes that have the same frequency, I'm probably not so happy about, saying that there are 3 modes for this data set, or saying that it's, if there were only 2 that tied, saying that it's bimodal. Might not be so happy with saying that in a case like this. So when we don't have a ton of data relative to the number of classes we have, or if we have a distribution that is pretty uniform, maybe the mode isn't such a great measure of center. Maybe it doesn't behave the way we'd expect. Now, if we were in a situation where we had categorical or nominal data and it was kind of still a uniform distribution, more or less, about the only thing that we can say about that in terms of a measure of center is the mode. So I suppose we're kind of stuck with using it there. But if I had something like die rolls where I do have a natural ordering, I might even argue that I have something close to ratio data, possibly, depending on context. But in that case, I might want to shy away from the mode and stick to, say, a mean or a median. That might be a more meaningful measure of center. So some positives, but also some downsides for the mode. Okay, let's talk about the geometric mean. So the geometric mean, I think we'll work through a motivating example to kind of show you where it comes up, but it's important in a few different contexts, but probably the most commonly kind of applicable context is in finance. So let's say we have an investment, and at time 0, we have $100 in our investment account. Now let's say that year 1 is a good year. Year 1, we have a rate of return for that year of 50%. So at time 1, if we have a rate of return of 50%, we get to keep our original stake and we get 50% more. But year 2 is not so good. We get minus 50% in year 2. Now, if I consider these percentages as data points like x1 and x2, I might be tempted to just average them together and say, okay, on average over these 2 years, I got plus 50%, minus 50%, average the two, they average to 0. I might be tempted to think that at time 2, I just end up back at $100. I had net 0 rate of return. But if I lost 50%, this is a plus 50%. If I lost 50% in year 2, that means I took what I started with at time 1, and at time 2, I only had half of that. So I started with 150. At time 2, I have 75. So saying my average rate of return is 0, that probably doesn't correspond with the behavior that I would expect from a statement like that, right? In this case, I ended up losing $25 over the course of those 2 years, not breaking even over those 2 years. So what's really happening if I give this, say, the number a, or the variable a of t looks like, and call it a naught, it looks like a bunch of 1 plus rates of return multiplied together. Or in this particular example, a of 2 is 100 times 1 plus 0.5 times 1 plus negative 0.5. So really what's happening here is these contributions are coming in multiplicatively. They're coming in as a geometric progression, it's called, instead of an arithmetic progression. So really what I would like to do, I would like to respect that geometric progression, that multiplicative idea that's kind of going on in the background here. So I would like to find a mean rate of return, let's just call it R, so that if I got that constant rate of return every year for these 2 years, that I would have the same amount at the end. That's what I would like to be true of a mean rate of return, right? That's kind of what was true of the average, is that if we replaced each of our data points that are kind of all over the map, if I replaced each of them with the average data, the average of the data, then the sum of the data would still be the same, whether I use everybody as the average or everybody scattered about. So same thing here. If I replace my variable rates of return with this quote mean rate of return, I would like to choose a mean rate of return that sets these two equal. So I see I have 1 plus r squared is 1 plus x1, 1 plus x2, or I have 1 plus r is the square root of 1.5 times 0.5. And if I calculate that on the calculator, I'll just keep my screen share the same, but you can do this on your calculator. So if I do square root, so that's second x squared of 1.5 times 0.5, that gives me about 0.866. And then I'd like to subtract 1 over, so my mean rate of return is 0.866 minus 1 is 0.134. Oh, with a minus. So had I lost 13.4% per year, what would my time to amount look like? So this is time 0, 1, 2 amount. We start with 100. The first year I lose 13.4%. So I'm down to what? 86.6. And then if I lose 13.4% again, I end up with 0.866 times, and then 1 minus 0.134. And that gives me 0.74995, or right on 75. So if I were to take these variable rates of return and kind of level them out, make them the same rate of return, I see that 13.4% loss, that would be the correct way to think of the average rate of return in this sense, where after 2 years, I would be at the same place, whether I use the variable rates or the constant rate, the mean rate. So this is what we call the geometric mean rate of return. And for a general data set, y1 through yn, that are all positive numbers, the geometric mean is the product of all of those data points to the 1 over n power, the nth root. Now, I am saying that this is a mean. We would kind of expect it to be related in some way to the arithmetic mean. And it does turn out that this is related to the arithmetic mean. So this is kind of an aside. If we log the geometric mean, we log the product of y1 through yn to the 1 over n power. As an aside, if you're not familiar with the log, not a big problem. This is just kind of this is just a little extra information to show you how the geometric mean relates to the arithmetic mean. One of the properties of the logarithm is that powers inside of the log become products outside. And another property of the log is that the log of the product of things is the sum of the logs of the things. So what I see is that the log of the geometric mean is the average of the logged data points. I can take the log of each data point or each data value, take the log of each of those, and then average that transformed data, and that will give me the log of the geometric mean. So the log of the geometric mean is the average, the arithmetic mean of the logged data. Okay, another mean that comes up occasionally is the weighted mean. So when we computed the arithmetic mean or the median or the geometric mean, any of those, kind of each data point was equally weighted inherently. Each one was equally important, as important as all the other ones. The weighted mean, though, says, what if I have data points x1 through xn that have different weightings, w1 through wn? So these are my data, and these are my weights. Where might this come up? Well, one place that it might come up is, say, global temperature data. It's kind of an important thing to know what the mean global temperature is, the mean temperature on the surface of the Earth. It's going to be hotter in some places, colder in other places. What is the mean temperature? We maybe would like to know that to see, things like global warming data, some of that kind of stuff. Well, I have a little bit of an issue in that, I have areas like, say, the US. I have areas like, say, the US where I have tons and tons of weather stations in here that might be recording data. But then I have other areas like in the middle of the Atlantic Ocean where I have far fewer weather measurements, right? Far fewer temperature measurements. So if you think, around Pittsburgh, I don't know, let's just say that we have 10 weather stations around Pittsburgh reporting temperature. Well, each one of those weather stations is going to be responsible for a relatively small area, a relatively small geographic area, right? Say like 1/10 the size of Pittsburgh or something. But each one of these, whatever weather buoys or something out in the middle of the Atlantic Ocean is going to be responsible for providing an estimate for a much larger swath of the surface of the Earth. We just don't have as many data points out there, so each one of them should be overweighted relative to the areas where we have a denser population of data. So I should probably give, say, each of these, 10 weather stations in Pittsburgh, let's say, a fairly low weighting because each of them is only responsible in a sense for providing information about a small geographic area. And things like maybe these weather buoys or something out in the middle of the Atlantic should get a much larger weighting because there are fewer of them. They're each responsible for giving an estimate for a much larger geographic region. Another place that we see weighted mean quite a bit is in grading criteria and syllabi. So let's look at an example where, let's say, the final exam is worth 20% of the course grade, the let's say there are quizzes that are worth 10%. Let's say there's a midterm exam that's worth 20%, and homework is worth 50% of the course grade. So these are the weights of each of these, right? So it doesn't matter just what 4 average grades I get for these numbers. It matters which one corresponds to which one, right? If I got a really high homework score and a really low quiz grade, I would prefer that, because that low quiz grade is going to hurt me less than if it was the other way around. If I got a low homework score and a high quiz grade, you know, that low score on something that's weighted at half of the value of the course is going to be much more detrimental. So maybe I would say my grade, let's say on the final exam, was a 90, the midterm was an 80, quizzes, let's say, is 100, and homework is 75. And these are all percents. So my particular grades are my data points, x1, x2, x3, x4, and each one of those is associated with a specific weight. So what's my final course grade? My grade is the weighted mean of these 4 data points, weighted by these weights. And how do I do that? I find the first weight multiplied by the first data point, second weight multiplied by the second data point, and so on through the nth weight multiplied by the nth data point, divided by the sum of the weights. Now, something to notice is if all of the weights are equal to 1, we just get x bar back. In the denominator, we get n, because we're adding 1 to itself n times. And in the numerator, we just get x1 plus x2 out through plus xn. And really, in fact, if the weights are all the same, even if they're not all 1, if the weights were k, let's say 3 or something, I'd get 3x1 plus 3x2 out to 3xn, but then I divide by 3 plus 3 plus 3. And I see that I could multiply numerator and denominator by 1/3, as long as I multiply top and bottom by the same thing, I'm okay. And the 1/3 would distribute, it would divide out all of the weights in the numerator. The 1/3 would also divide out all the weights in the denominator and just leave us with ones. So really, if all the weights are the same number, we still get x bar back. I suppose we probably don't want weights to be 0, and it probably doesn't make a whole lot of sense to make weights negative numbers. But if we're thinking of positive weights, then we can make these 2 statements. Well, really, this statement, the more general one. If the weights are all the same, we get x bar back. So x bar is a special case of a weighted mean, or the weighted mean is the generalization of x bar, the arithmetic mean. So what would my grade be here then? It'll be the first weight, which I'll write as 0.20, times the first grade of 90. And I'll just keep in mind that the answer at the end is going to have units of percent, because that's what my grades units are. A weight of 10% times 100, a weight of 20% times 80, and a weight of 50% times 75, divided by the sum of the weights. And in this case, the weights sum to 1, so we can get rid of the denominator. And if we do this calculation, we get 0.2 times 90 plus 0.1 times 100 plus 0.2 times 80, and then plus 0.5 times 75, we get 81.5. And my units are percents, so 81.5% for my grade. And using this basic idea, we can, ask questions like, well, let's suppose that I'm near the end of the semester. I don't have my final grade yet, my final exam grade yet. And I want to know how well do I have to do on the final exam to get an A? Well, I replace this by a variable, let's call it maybe Y. And I set this equal to 90%, and I solve for Y. I could ask, like, what is my approximate grade, say before the final exam? But would that change? Well, I'm not taking into account the final exam at all, so I would leave off this term, but also this weight. So I'll use maybe these three, 0.1 times 100 plus 0.2 times 80 plus 0.5 times 75, but then divided by the sum of these three weights, which is only 0.8. In other words, out of an 80 possible percentage points that I could have earned so far in the course, what proportion of those 80 percentage points did I earn? That's why I'm dividing by 0.8. So that's the weighted mean. And last is the harmonic mean. So let's look at a motivating example here. Let's say that I go on a road trip and I travel at a speed of 60 miles per hour for 1 hour. Then I travel at 30 miles per hour for 1 hour. What is my average speed? Note that I traveled for equal time in this case. So equal time. Well, I could compute average speed in two different ways. Maybe I do, I'm not sure if this will work, but let's see if it does. Maybe I do 60 plus 30 over 2 is 45 miles per hour. Or I could just do this the long way, right? I know that how far did I travel this first hour? So this is 60 miles per hour, 30 miles per hour. How far did I travel the first hour? I traveled 60 miles. How far did I travel the second hour? I traveled 30 miles. What was the total amount of time that it took me to travel 90 miles? 2 hours. So this is 90 over 2 or 45, and my units are miles per hour. So I can compute the arithmetic mean of my two data points, 60 and 30, or I could do it the long way, and I actually do get the same answer. What if my data was reported slightly differently? What if I had traveled 60 miles per hour for, let's say, 60 miles, and I traveled 30 miles per hour for 60 miles? So here I've got equal distance at each of these speeds. If I do the same thing, do I get the right answer? Well, my X bar is 60 plus 30 over 2 is 45 miles per hour, seemingly for my average speed. Is this consistent with what actually happened? Well, how far did I travel? I traveled 60 miles plus 60 miles. I traveled 120 miles. And how long did it actually take me? Going 60 miles an hour for 60 miles took me 1 hour. Going 30 miles an hour for 60 miles took me 2 hours. So it took me 3 hours to go 120 miles. Or this is 40 miles per hour. Note that these are not equal. So if I travel different speeds for equal distances, I can't just average the speeds together. If we thought of an extreme case, what if I had said 0 here, and if I had said 0 here? If I drove 60 miles an hour for 1 hour and then parked and ate lunch or something and drove 0 miles an hour for 1 hour, does that make sense? Sure. It would just have taken me 2 hours to go 60 miles. I'd have driven an average of 30 miles an hour, 60 plus 0 over 2, just fine. But what about this one? Can I go 0 miles per hour for 60 miles? If I'm not moving at all, how long will it take me to travel 60 miles? It'll like take forever, right? This seems like it should take like infinite time or something like that. So we clearly see that this is a different structure we're working with here. If we travel equal distances at certain speed versus equal times. Equal times, we can average things like normal. Equal distances, it turns out that the harmonic mean is the way to go. The harmonic mean is n over 1 over x1 plus 1 over x2 out through plus 1 over xn. Or another way to look at it is that 1 over the harmonic mean is the average of the 1 over the data. So 1 over the harmonic mean is the average of the 1 over data points. Feels similar to the geometric mean, right? Where the log of the geometric mean is the average of the logged data. Here, 1 over the harmonic mean is the average of 1 over the data. So let's try this with this data up here, where we had 60 and 30. Well, I have 2 data points. And my data are 60 and 30, so I have 1/60th plus 1/30th. Well, I want to, in the denominator, I want a common denominator of 60, so that's 1/60th plus 2/60ths over 60. So that gives me 60 times 2 over 3 when I flip my fraction of the denominator. 120 over 3 is 40 miles per hour. And that does mesh with what I would expect. So that's the idea of the harmonic mean. When my data points are represented in such a way that, say, for speeds, they're representing equal distances traveled, I want to use the harmonic mean as a measure of center, because if I use the arithmetic mean, I still can compute it. I can add 60 plus 30 over 2, that, nothing blows up. But I get a number out that is not really that is not really helpful, right? The idea of what is the average speed that I traveled is, if one car was driving a variable speed and another was driving a constant speed, what speed would the constant speed car have to drive so that they both get to the destination at the same time? Okay, so that wraps up section 1. The video is getting a little long, so we might actually do, I think we actually will leave 3 for class on Tuesday, and we'll talk about a little bit in 3.2, but I think we'll leave all of 3.3 percentiles and so on until Tuesday's class. And we'll also do salary and probably the Brandon data as well, variance and standard deviation in Tuesday's class. We'll just go through another example of computing each of those by hand. So a couple of ideas. So we talked about the range. Which is x max minus x min. We talked about the variance and the standard deviation. The variance was a nice measure. It had some nice properties to it. The variance is more or less the average squared deviation from the mean. So we found the mean, we took deviations from the mean. How far away is each data point from the mean? We squared it to make the negative ones positive. And then we essentially averaged it, right? We divided by n, or perhaps n minus 1 in the case of the sample variance. The problem, though, was with the variance, when we square the deviations, we end up with squared units. We want units of the original data so that we have sensible units. So the standard deviation is the square root of the variance. That puts us back in the units of the original data. And that's probably a better measure to report as a descriptive statistic. The variance does have some nice mathematical properties, so sometimes we'll work with the variance and other times we'll work with the standard deviation. The standard deviation, though, does have units, right? It has units of the original data. So if I want to compare between data sets and say maybe I think this data set is more variable than that one, if they're not in the same unit, either explicitly, like say degrees Fahrenheit versus degrees Celsius, or implicitly, like 1920 US dollars versus 2020 US dollars, maybe we want to do something to kind of cancel out those units. Maybe we want to get rid of the effect of those units or the general size of the data sets, the effect that that's having on the variation. And that way we can maybe compare two data sets that have some inconsistent units or some size inconsistencies directly to one another. So the measure that will help us here is the coefficient of variation. We're not going to talk a ton about it, but the coefficient of variation, well, I want it to be a measure of variation. So it should get bigger as things like the variance and standard deviation get bigger and vice versa. So I want it to kind of look like the standard deviation. But the problem I have with standard deviation is it has units of the original data. I would like to divide out those units, and I would also like to just scale out the general size of the data so that if I just, change how I'm measuring the data, if I'm measuring salaries and say some number of thousands of dollars versus just number of dollars, like if I write my data points down as 28,000 or as 28, I don't want that to have a big impact on my, say, standard deviation whenever I'm comparing across data sets. So I'll divide by the mean. The mean has units of the original data, and it's also kind of the size of the typical data point. So the mean, if I'm reporting salary like 28,000, is going to be 1,000 times as large as if I'm reporting salary like 28 with the units of thousands of dollars. Or of course, S over X bar if we were using samples. And we'll look at some examples of coefficient of variation when we compute some measures of center and variation in Excel. But that's the idea of coefficient of variation. It is unitless, and it scales out the general size of the data, allowing us to compare variability between different data sets. I can compute, this or that data set's coefficient of variation and see which one is larger. That's going to give me a more sensible idea of which data set is more variable than if I was to say compare their standard deviations or something directly. So the next minor topic that we have to go over is Chebyshev's theorem. So Pafnuty-Chebyshev was a Russian mathematician and statistician. His name obviously was in Russian in the Cyrillic alphabet, so the transliteration to English letters is, all over the place. Sometimes there's a V at the end, sometimes this is a CH, sometimes this is a V. So there's lots of ways to transliterate his name. But if you see something that looks like Chebyshev, it's probably the same guy. So Chebyshev's theorem says the following. For any data set, the following is true. The proportion of data points that have a value within k standard deviations of the mean is at least one minus one over k squared for k bigger than one. So what are we saying here? We're saying, imagine a real line. Imagine that we have a mean, let's say x bar here. And maybe if I'm interested in the case k equals 2, maybe this is a standard deviation. And then there's a second standard deviation. This is x bar plus 2s. And I could do the same going to the left. So I see any data point that has a value in this interval of the real line will be within, in this case, 2 standard deviations of the mean. And any data point with a value to the left of that lower bound or to the right of the upper bound will not be within 2 standard deviations of the mean. So what percentage of data points have to have a value within 2 standard deviations of the mean? Well, that percentage has to be at least 1 minus 1 over 2 squared, 1 minus 1/4 is 75%. So Chebyshev's theorem is really it's a theorem, it's a statement that is always true. This is based on how the mean and standard deviation are defined. And in this case, Chebyshev's theorem says that there has to be at least 75% of our data points that have a value within 2 standard deviations of the mean. If we tried to construct a data set with more data points with values far away from the mean, then what would happen is either our mean would change or our standard deviation would change or both in order for us never to fall below 75%. So for different values of k, what do we get? The minimum proportion of the data that has to be within 2 standard deviations of the mean is 75%. For 3 standard deviations, we have to have at least 89% of our data points with value within 3 standard deviations of the mean. And for 4 standard deviations, 93.75%. So I see as I increase K, I'm covering a wider and wider swath of the real line. And then a higher and higher percentage of my data points have to fall in that interval. This might not seem like a really important idea, but it will actually be important for some of the things that we talk about in the future. So some of the other theorems we talked about, law of large numbers or central limit theorem, some of these ideas will kind of lean heavily on Chebyshev's theorem. The other thing that I want to mention is this is a theorem. It can be proved. We're not going to prove it right now. We're going to wait until the end of chapter 4. At the end of chapter 4, we'll have built up a little more vocabulary and a little more mathematical structure, and that'll just make it easier to prove. So we'll revisit this at the end of chapter 4. We'll go through the proof. It's not a very complicated proof, but it's just that once we hit the end of chapter 4, we'll have a little more exposure to some things like probability, and we'll be able to go through the proof, I think, a little more easily at that point. So proof at the end of chapter 4. So 2 more ideas in section 2, and then we'll do the Excel examples, and then we'll be done for the supplemental video. So the next idea is a little bit like Chebyshev's theorem, but it's actually very widely used. That's an important idea. And it's the empirical normal rule. And it says the following. It says, if a data set is approximately bell-shaped, note that Chebyshev works for any data set. It could be bimodal, it could be, crazy looking. For any data set, Chebyshev's works. But for the empirical normal rule, we need approximately bell-shaped data. When we talked about distributions, we said bell-shaped data actually comes up quite often. So we can use this quite often, but we do have a condition here. So we want to check this. We want to have an idea of whether or not our data set is bell-shaped. And if we think that it is approximately bell-shaped, we can then apply the following conclusion. And as I mentioned before, the bell-shaped distribution is also called the normal distribution, which is where the normal in the empirical normal rule comes from. So if the data set is approximately bell-shaped, then approximately 68% of the data points are within 1 standard deviation of the mean. Approximately 95% of data points are within 2 standard deviations of the mean. And approximately 99.7% of our data points have a value within 3 standard deviations of the mean. So Chebyshev applies to all distributions, and it guarantees that at least 75% of data points will be within 2 standard deviations of the mean. But for reasonably nicely behaved distributions, we see that it's really about 95% of our data points that'll be within 2 standard deviations of the mean. Or an analogous way to phrase this, Chebyshev would say no more than 25% of your data points can be more than 2 standard deviations away from the mean. And the empirical normal rule would say for nice data, for bell-shaped data, no more than 5% of your data points are likely to be more than 2 standard deviations away from the mean. And then similarly for 3 standard deviations. Chebyshev says for any data set, basically no more than 10% of your data are going to be more than 3 standard deviations away from the mean. But the empirical normal rule says, well, for nicely behaved data, for data that fits reasonably into a bell curve, only about 0.3% or only about 1 in 300 data points is actually going to be more than 3 standard deviations away from the mean. So Chebyshev is a guarantee it applies to any data set, but the empirical normal rule is much more useful. Chebyshev is kind of overly conservative. But Chebyshev being a guarantee is important for some of our future theorems. We want to have that kind of solid bedrock to build theorems off of. But if we're using this in any kind of, applied setting, a rule of thumb like the empirical normal rule is going to be much more useful most of the time. And then lastly, we have a range rule of thumb. And that is that the range is about 4 standard deviations. Or in other words, a standard deviation is about 1/4 of the range. I introduced this because we'll kind of see this idea pop up in the next section. This is usually a pretty terrible estimate of the standard deviation, though. It'll probably get you like the right order of magnitude, but that's probably about it. So not a great estimate, but we'll see this general idea that something like, roughly speaking, a data set spans about 4 standard deviations. We'll see that kind of idea come up when we talk about outliers. Okay, so the last thing that I have planned for today is to just quickly go through this Excel demo, and then we'll call it a day. So we went through the measures of center in class on Tuesday, but let's go through them again. Remember, we have the Ashley population, we have the Brandon population that's named Brandon. And I always do this in Excel. Whenever I want to get out of a cell, I hit escape, but escape pops up my Zoom meeting controls. So I don't know how many times I'll do that, but if you see me pausing for a minute, I'm fixing my Zoom controls that seem to sometimes randomly pop up, and I'll just stop and fix them. And then salary, this data set is also named salary. You can see on the top left here. As usual with Excel, if we wanted to compute something, we start with equals with an equal sign. I want to use a built-in function average. And then I'll just select my data. I'll end the parentheses. And I see my mean of my Ashley data was 8. I can click and drag over, and I see that now I'm selecting the Brandon data. I don't want to drag again because I'll miss this last one, but I can refer to this data set as salary, which I named it, and that makes it easier for me to refer to. For median, I have median of the Ashley data, median of the Brandon data, oh, got an extra parentheses in there, but that shouldn't hurt anything, and median of the salary data. And for mid-range, it's the average of the max and the min. Max and min are both Excel functions. I need max plus min over 2, but I need the max and the min in parentheses. So I'll start with 1 parenthesis. Maximum of the Ashley data plus minimum of the Ashley data. I'll close my numerator parentheses, divide by 2. And I can drag this across. I see that my Brandon data looks right. I see that my salary data, I'm missing one, but I can actually adjust that. I can, if you look at this box, when I hover over the edge of the box, it kind of lights up. And if I go down to the bottom right corner, you see my cursor changes to this little diagonal arrows. I can double click that and drag down. And I can do that again to select the, can't seem to select the one inside of the min very easily, having cursor issues, but I can just expand that by one unit on that box to select the salary data. Right. So a few different ways you can go about doing this. For range, we need max minus min. So the max of the actually data minus the min of the actually data. Range of the actually data is 6 returns per day. I can also use the fact that I've named my Brandon data. So I see Brandon's data has a range of 11 units, so nearly twice that of Ashley's. Since Ashley and Brandon, their data have the same explicit units, but also probably kind of the same implicit units. They are both working for the same accounting firm, both returns per day, and right. Maybe at this point we'd feel comfortable saying, well, it looks like Brandon's data is maybe about a twice as variable as Ashley's. But I would not want to, when I calculate the range for salary, I wouldn't want to make that comparison directly to, say, Ashley or Brandon. So max of the salary data minus min, minus min of the salary data. So I see the range of the salary data is $72,000, right? Different unit from the Ashley and Brandon data explicitly, but also implicitly, right? Just the general, size of this data is much different than the size of that data. So variance. We mentioned in class that there's population variance and sample variance, and that they're not calculated the same way. So sample mean and population mean, they get different notation, but they're calculated the same way. So we just use the same function average for all of them. But for variance, we need two different Excel functions. The Ashley and Brandon data are populations. So equal VAR, this is the variance. And then I see I have V, it's a little hard to see on the screen. Unfortunately, I can't blow up this little box here where it explains things, but if you do VAR, you should see this pop up. First two options should be VAR.P and VAR.S. VAR.P calculates variance based on entire population. VAR.S estimates variance based on a sample. Ashley and Brandon are populations, so I want to use VAR.P. So I want the population variance for this data set. And we see we get 4. Remember that variance is always in square units, so this has 4 returns per day squared. Not a very sensible answer, but I could square root using the SQRT built-in Excel function that variance to get 2. Right, that gets me the standard deviation. I'm back in returns per day, so Ashley's standard deviation 2 returns per day. Ashley's coefficient of variation is her standard deviation over her mean, or 0.25 in this case, 2 over 8. That's a unitless number for coefficient of variation that allows us to compare across data sets. For Brandon, again, VAR.P, because the Brandon data is a population. And I can use my the fact that I've named my data Brandon. I could square root to get the standard deviation, or if I wanted to, I could use the stdev built-in Excel function. Now, of course, there's sample standard deviation and population standard deviation for the same reason as the variance. And I want to make sure that I use the population standard deviation in this case because the Brandon data is a population. I can use the name for the data, Brandon. And I see I get 4, right? Just as I would expect, square root of 16 is 4. Just like with actually the Brandon variance of 16 is in returns per day all squared, but Brandon's standard deviation is 4 returns per day. And his coefficient of variation is his standard deviation over his mean, or 0.5. So looking at either of these numbers, these, because we have the same units explicitly and implicitly between Ashley and Brandon, or looking at the coefficient of variation, we see that Brandon's performance is about twice as variable as Ashley's. We also saw that in the range up here. For the salary, let's calculate the variance. Now I want var.s for sample variance. The salary data is a sample. And again, I can drag and select, or I can just start typing in salary, hit tab to complete. The variance of the salary data is this 843 number, and that's in thousands of dollars, but all squared. So millions of square dollars. Doesn't make a whole heck of a lot of sense. So we compute the standard deviation, stdev.s, sample standard deviation for the salary being a sample. I'll start typing in salary and then tab to autocomplete. Close the parentheses, and I see now my standard deviation is in units of the original data. $29,000 is the standard deviation for the salary data. Now note that if I'm going to compare the salary data's variability to Ashley's or Brandon's, I don't want to compare these 3 numbers and say something like, well, it looks like the salary data is about 15 times as variable as the Ashley data and 7 or 8 times as variable as the Brandon. I don't want to do something like that, right? Because these are explicitly different units, and certainly the data are just of a generally different size. But I can compute the coefficient of variation, standard deviation over the mean. That will get rid of the explicit unit, but also scale out the size of the data generally. My coefficient of variation for the salary data is about 0.65. And so I see that the salary data is more variable than Brandon by, what is that, 15 percentage points on a scale of 50, so maybe like 30% more variable. And it's maybe about, so 25, so 0.25 to 0.64, 2.5 times as variable as the Ashley data set. So I see that the salary data is inherently more variable than Brandon or Ashley because it has a higher coefficient of variation, which does divide out the unit and take care of the scale of the data. As an aside, as I mentioned in class, this is on Blackboard, this Excel file, so you can download this, you can work along with all of this if you haven't already. So here's an example of weighted average where we have different grades along with their weights. And 2 ways we can compute this. We can compute this the long way, where I take grade 1 times weight 1 plus grade 2 times weight 2 plus grade 3 times weight 3 divided by the sum of the weights. In this case, if I didn't divide by the sum of the weights, I end up dividing by 1, I would still get the same answer, but it is good practice to write the formula correctly. And that way, if you go in there later and you change something, if you say, oh, actually, I wanted this to be a 0.1, this does update. The other thing I can do is I can use a built-in Excel function called sum product, where it does this idea for me. I enter two lists, and it goes element by element through each list, multiplies the two together, and then after it multiplies, it adds everything. So this is actually the reason this is a built-in function is this is an example of something called an inner product that's a structure that's used all over the place in math. So this general concept of an inner product is an important idea. So that's where the sum product built-in function comes from. It just happens that it works nicely for weighted means. But this idea of an inner product, this weighted mean idea, we can really think of the weighted mean as being literally a center of mass for certain masses at certain positions. So where the positions would be given by the x's and the masses would be given by the relative weights. So if we think in terms of like physics or something, from high school, this really is like a center of mass idea. Okay. Oh, and I should note that the sum product only does the numerator. So I guess probably technically I should be a little more careful and do divided by the sum of the weights. I really ought to do that. So now if I go and change this guy to 0.1, right, now these both update the same. I was being a little lazy with the sum product because I knew the weights all added up to 1. And then here's an example of geometric mean. If I have a mutual fund that over 4 years, the first year it returned 5%, the second year 10%, then 15%, and then 20%. I don't know why I have data and 1 plus data here. Let me just get rid of these. I think I was showing something else to a different class. But if these are my 1 plus rates of return, then my geometric mean of the 1 plus rates of return, I can find with geo mean. So this is a built-in function in Excel that gives me the geometric mean of the things I enter. So I want the geometric mean of that data. And this gives me 1.12. But remember, it was like 1 plus the geometric mean, 1 plus the geometric mean rate of return was what I ended up finding. So really I had to subtract 1 from this to get a sensible geometric mean rate of return. So in other words, had I gone through these 4 years and gotten the variable 5% gain in the first year, 10% in the second, 15, and then 20 in the next 2, or had I picked a different investment that say got 12.4% gain every year for each of those 4 years, the same gain every year, I would have ended up with the same amount of money at the end of those 4 years, either way, whether I got the variable or the fixed rate of return. Of course, if I average these, the average will be 12.5%. My geometric mean is always going to be less than my arithmetic mean, the mean or the average. Geometric mean is always going to be less. The more variable my data is, the more it kind of, sawtooths up and down, especially if some years I have negative rates of return and some years positive. That pulls those two means further apart. So my geometric mean can actually end up significantly different than my arithmetic mean under some circumstances. Okay, so I think that is all that I had for the supplement video. I know it went a little bit long, and we are just going to push section 3.3 until Tuesday. We'll just take time on Tuesday's class to go through 3.3, and then get a little bit less of a start on chapter 4 than we would have otherwise. But we still have we're still fine as far as the schedule goes. So we will end it there today, and I will see you on Tuesday.